Thank you very much for inviting me to give this talk. I understand I have to say something to Jay. So I have a full slide of Jay. Basically, I want to put Jay in historical perspective, my historical perspective. So in the beginning was Mark's building. Remember? It was basically a plasma physics lab, which was founded by Avive and Dotan Zal. I joined the group in '82, then came Baruch Meyerson, then Arias Ziegler, but basically we stayed more or less plasma physics group, although Baruch brought some nonlinear dynamics from Moscow. And then Jay joined our group, and led to a much greater diversity in experiments because he moved in completely different direction. Diversity is a good word in America now, is it? Okay, so we diversified our group, and then came Eran Sharon, Omri Gat, Eitan Katsav. So we are a small group, but we are working in many, many different directions. From time to time, we collaborate, and this is an example. And I think Baruch mentioned this work. Again, Faraday waves. I didn't know that Faraday waves are so fashionable this day. So in this experiment, Jay collaborated with Baruch and their students in exciting Faraday waves by passing through slowly passing through resonance with these waves. So this is a good starting point for my talk because this is the only thing I want to discuss. What happens to a system when you drive it by an oscillating force and slowly pass through a resonance with some wave or oscillation of the system. So here we have my talk. This is the outline. I basically want to illustrate what happens. And the claim is that by passing through resonance, you can incite all kinds of very non-trivial patterns. I'll talk about basically 4 examples. The first is the autoresonant pendulum. Then we'll discuss formation of M-fold symmetric vorticity states, excitation of multiphase waves of the Korteweg-de Vries equation, and if I'll have time, I'll talk about giant ion acoustic waves. So this is my first example. You may ask a question which sounds like a trivial question, but it has quite a complicated answer. How to excite a pendulum by studying in equilibrium by applying a small perturbation and excite the pendulum to very large amplitudes. It seems to be counterintuitive because we know by using perturbation theories that when you use a perturbation, the effect is very small. So the answer of how to, I'm sorry, I moved too fast. So the answer to this question is basically to drive your pendulum. I don't know why it moves so. Okay, let me try again. So this goes here, so but the light doesn't work. So we have a mechanical system. Okay, so you start with a pendulum, you drive the pendulum by an oscillating force, let's say constant amplitude, but the frequency of the force is slowly varying in time, and at t equals 0 passes the linear resonant frequency. So this seems to be a very simple problem, but actually its solution or analysis is very, very complicated. What we can do, we can simulate the system very simply, just to use a MATLAB program. And here is the result of the solution of this equation when I'm using some parameters for the driving amplitude and the chirp rate of the driving frequency. Note that the amplitude of this perturbation is very small, and the chirp rate is also very small. The result that I'm getting in this simulation is shown on this graph. I show here the energy as a function of time. Remember, we pass the linear resonance at t equals 0. We start somewhere above the resonance. And then at t equals 0, we see, look at this blue line, we see the excitation of the pendulum oscillations of the pendulum, and it reaches this energy of 2, and this energy corresponds to the rotation of the pendulum. So we start in equilibrium, and we excite it to very large energies. Somewhere here we have transitioned to chaotic motion, and one can see that this is chaos because this blue line actually describes 10 different trajectories with different initial conditions. So you see that the trajectories separate very strongly here, and it's a real transition to chaos. Now there is another detail which is very non-trivial, that this kind of very large excitation by using a small perturbation one gets only when the driving amplitude exceeds the threshold value. And this is a number for this system. Actually, this threshold phenomenon was discovered experimentally. And only then we understood the theory behind that. It was discovered in the lab of Joel Fagans at UC Berkeley quite a long time ago. Quite surprisingly, this threshold scales as the chirp rate to power 3/4. Now, I did mention another fact that when you have this very large excitation, this pendulum is actually phase locked to the drive. So the frequency of the pendulum of these oscillations is more or less following the varying frequency of the driving the driving force. Below the threshold, you dephase and the excitation saturates. I want to show you the experimental system which was used to find this phenomena, this threshold phenomena, and this is, of course, this is not a pendulum, but actually Fagans used trapped electron clouds. You create these clouds, and people usually call it non-neutral plasma. This is basically an electron cigar. You shoot an electron beam along a magnetic field, strong magnetic field, and then at some time you put these negative potentials and cut a piece of the electron beam, which is now trapped in this trap. So because of the strong magnetic field, these electrons cannot move across the field, so they cannot leave this trap. And in this direction, it's confined by these electrostatic potentials. Now, if one wants to study this problem analytically or mathematically, one has to solve what's called drift-Poisson system. People who study plasma physics know that since this cloud is charged, there is a radial electric field in the system, and there is this axial magnetic field, and in this situation, charged particles perform what's called E cross B motion, which is a drift. This is the drift velocity. It's azimuthal, and it's a product of the electric field feeds the electric potential and the direction of the magnetic field. And since this velocity flow is incompressible, this electron cloud is described by this particular system. The first equation is just the continuity equation for the electron density, and then this velocity is basically given by the electric potential, and the electric potential is defined by the Poisson equation. What is interesting about this equation, that actually this equation is isomorphic to Euler's equation for 2D ideal fluids. In this case, we describe a rotating velocity field, which is given by the stream function psi. And you see that this expression is very similar to this one. The vorticity of this field is curl of V, so it has a value of Laplacian of psi in 2D, and it's in direction of Z, direction of this magnetic field. And the Euler's equation are written here. This is the continuity equation for the vorticity, and this just comes from the definition of the vorticity. So these equations are the same. So people who are doing experiments with these electron clouds are basically doing experiments with 2D ideal fluids. And this is the analog. Vorticity is like the density of this cloud, and the stream function is like the electric potential. If you say with the Euler equations, one can ask what are the solutions of these equations. One finds that there are many solutions. as usual with the PDEs, but one of the simplest solutions is the solution where the vorticity is constant inside the circle, the vorticity is 0 outside, and the whole circle, or the cross-section of this fluid performs solid body rotation with frequency which is half of the vorticity. An interesting question is, are there other non-circular, uniformly rotating constant vorticity or electron density equilibria? And the answer is yes. There are so-called V or vorticity states which were discovered by Dima and Zabusky quite long ago. Another question is how to create these non-trivial vorticity states by using a small perturbation. And the idea is very similar to what we have done with a pendulum. One has to pass through resonance and synchronize. The way this is done, let's say for the electron cloud, is that this is the cross-section of the electron cloud. You apply a quadrupolar potential and you oscillate the potential with a slowly varying frequency. Okay, so this is the applied potential. It creates this kind of distribution of the potential inside this vessel, and you slowly pass through resonances with different V states. This is linear resonant frequencies. What you find if you do the simulations, you find the following behavior. For example, to excite M equal 3 state, where you apply, instead of the quadrupolar potential, you apply a sextupolar potential. You start with the circular vortex, and then you create this triangular M equal 3 V state. If you apply another potential with a different symmetry, you're getting this M equal 4 and M equal 5 states. Well, I'm not sure if people ever saw quadratic vortices or pentagons. In any case, one creates a complicated, non-trivial patterns by slowly passing through resonance. This was my second example, and now I go to the third one, which is about multiphase nonlinear waves. Now we know that there are traveling wave, nonlinear wave solutions where the solution is a function of one phase, kx minus omega t. We have many examples of such waves, but not everybody realizes that there are other solutions in many nonlinear systems where instead of one phase, you have many phases, maybe additional phase or the third phase and so on. And actually many nonlinear systems or many famous nonlinear PDEs have these kind of solutions. So the question is how to excite a multi-phase wave of, let's say, the Caudy-de Vries equation. Now the Caudy-de Vries equation is written here, equal to 0. And the solution to this problem of excitation of multiphase waves is driving this system by a combination or superposition of simple waves. If you want to excite two phases, you drive it by a superposition of two waves, each one having its amplitude, but the frequency is chirped and passes through a particular linear resonance with the unperturbed KdV equation. Now the KdV equation describes many physical phenomena. It describes, for example, surface waves on shallow water, describes also ion acoustic waves and plasmas and many other phenomena. So this is very general type of problems. Now, I show you here a numerical example where we excite, by using this method, we excite a three-phase wave of the KdV equation. The wave is actually shown here. On this graph, I show the value of U, of the solution, at a certain point as a function of time. When we look at this solution, it looks like noise. you wouldn't recognize that there is something which is organized here. The only thing one can see is that the amplitude of this solution is growing all the time. Okay? What we do, we use 3 waves with 3 slowly varying frequencies. Each one of them passes through a certain resonance with the unperturbed equation. If you want to see how the waveform looks at certain time or in a certain small time window, it's shown here. Okay, at the beginning it looks like a quite organized, well-organized wave, but at the end it looks like a stormy ocean. Okay, note also that the amplitude of these waves is huge compared to the perturbations, which is usually of the order of 1%. Now, how do we know that we actually got the 3-wave solution? What helps us is what is called the inverse scattering transform approach. Inverse scattering transform was discovered, quite surprisingly. This year it's the 50th anniversary of the discovery of this transform. This transform actually led to a revolution in the field of nonlinear waves because people suddenly knew how to solve many of these kind of equations, like the KdV, nonlinear Schrödinger, and many others. Okay, so this analysis allows to actually understand what kind of solutions you're getting. The analysis is quite complicated, but actually when you analyze your solution, you can first of all know how many phases you excited, 3, 2, or more. You can also calculate the frequency of these, each of these phases. And these are these omegas, large omegas, omega 1, omega 2, omega 3. I plot here the dependence of these frequencies on time, but I also plot the driving frequency as a function of time for each of these excited phases. And you see that at time equals 0, when we pass through these 3 resonances, you phase lock. The frequency omega 1 follows the first driving frequency. Here, the phase locking is stopped somewhere after passage through resonance because we were below the threshold. We took one of these epsilons too small, and here the phase locking continues. So we do excite these complicated solutions. Physicists know very little about these multi-phase solutions because they don't look nice. And therefore, I am not familiar with experiments where one can, in a controllable fashion, excite these multi-phase solutions in some of these nonlinear systems. Okay. Now I go to my 4th example. By the way, how much time I have? 5 minutes. Okay, I'll try to do it quickly. Now I discuss the evolution of ion acoustic waves in plasmas. Ion acoustic waves are oscillations of ions in the plasma in the self-consistent electric potential due to these oscillations. And this problem is described by what's called the Vlasov-Poisson system. F is the distribution, velocity distribution of the ions. So it's a function of the velocity of position and time. This is so-called Vlasov equation. The distribution is driven by the self-consistent potential, which is described by the Poisson equation. In the Poisson equation, you can see here the density of the ions. It's distribution integrated over velocity. You get the density of the ions. And this part is the density of the electrons. The electrons are very light and fast, so there is an assumption that these electrons are Boltzmannian. They basically feel the self-consistent potential, but in addition, we add the driving potential, which drives the electrons. Okay? So the electrons feel the slow self-consistent and slow driving potential. We assume that the driving potential has this wave-like form with slowly varying chirp frequency. There are very few parameters. Actually, there are no parameters in this equation. There are 2 parameters in the driver, but there is one important parameter in this problem, and this comes through the initial conditions. I assume that initially the distribution is a Maxwellian. And here there is this thermal velocity, ui, and there are two very different problems in the context of this chirp frequency driving. One is when this ui is relatively large, of order of 1, let's say 1, and one when this ui is much less than 1. One finds that the patterns you develop are very different in these two different cases. Okay, so let's start from the first case where this ui is 1, so distribution is wide. I show here the phase space, so this is velocity and x, and I drive initially my system at t equals 0 so that the phase velocity of the driver is somewhere in the tail of the distribution. Okay, and then as time passes, I decrease the frequency, so the phase velocity of the driver decreases, and one can see that I develop holes in phase space. And these are holes because of this bluish color, which means that the density here is low than the surrounding density. If I continue chirping my frequency, so I go lower in this VD, I drive this hole even deeper into the distribution. But you can notice that the position of this hole is given by the position of the driving phase velocity. Here and here, at the beginning, there is nothing. So in this first case, one gets holes in the phase space. One phase log these holes to the velocity of the driving force. And very different example is in the case when this velocity, the thermal velocity, is very, very small. In this case, initial condition is shown here in phase space. You see this is a Maxwellian, but it's very narrow Maxwellian. The driving phase velocity starts somewhere here, and there is a difference without increasing the driving frequency. So this alpha is positive, is plus sign here. And we slowly pass what is called the ion acoustic frequency. This is a linear frequency of ion acoustic waves. So the driving phase velocity moves up, and let's see what happens. We start somewhere at negative time. At t equals 0, we pass the resonance. And then, after the passage, we develop this kind of distribution. So it looks like kind of soliton, you may say. Okay, a little bit reminds us the KdV solitons. If I continue driving the system, I continue increasing this driving velocity, I get this kind of distribution function. It's actually very peaked. When this velocity is small, then this system can be also studied within the fluid approximation. So in the fluid approximation, you develop here a real singularity where distribution function is sharply peaked. It's called a picon sometimes. So you see, you drive in you chirp your frequency in a different direction. In these two examples, you get very, very different phenomena in each one of them. Okay, I think I finished my talk, so I have only my conclusion slide. Okay, so conclusions are rather simple. Okay, if you phase lock initially, many driven oscillatory nonlinear systems remain phase lock under a adiabatic variation of parameters. So you chirp, you don't lose this phase locking, and this is the way you can control your system. Starting in a linear equilibrium and passes through resonance guarantees this initial phase locking. For controlling this wave system, you have to first phase lock. If you start in a linear equilibrium, then phase locking may be very easy. You simply pass through this linear resonance with the system. And finally, the continued adiabatic synchronization is achieved by slow transformation in the system's solution space. So you travel in this solution space, and frequently you develop a variety of very non-trivial nonlinear patterns. Thank you.
Just a matter of how you plotted the data, but I would expect that when you're chirping on all the experiments, you should see something even for negative time. I mean, something that increases, except the effect on the other side is But
Yeah,
Charlie
but for-
Doble is that.
Yeah. So the question was what actually happens before you pass the resonance. Okay. What you find is a very interesting phenomena. The phase locking starts before you cross the resonance.
Oh, yeah.
So you phase lock almost immediately, and then you continually pass the resonance to develop all these nonlinear solutions.
So I think the model systems that you presented were all without dissipation, is that correct?
That's right.
Okay, so I guess, the underlying resonances that you have in your system have a quality factor of infinity. So the fact they get excited is not
Okay,
totally surprising.
so basically the question is what happens with dissipation? If the system is dissipated, what happens? The answer is the following. We have studied this problem. One finds that when the dissipation is sufficiently small, and there are some criteria, okay, when it is small, nothing special happens, you have the same phenomena. Dissipation even helps this phase locking. So you are phase locked and you kind of are on some attractor because of the dissipation. Okay? But when dissipation is large, the phenomenon is killed. Yeah. Dissipation typically leads to death. That's exactly what happens here.
Allows life as well.
Yeah. Okay.
Okay, well, thank you very much.
Thank you.